Dr. Bosa science, Kwano Kabeti science, Rafu ya Bosa science, Truth in Beta, Truth in Omega, Truth in Alpha science.
The Science Foundation College enamave ku Lwejjinja ng'oyingira kilomita emu. Somero lya Dene Boarding eri abawala n'abalenzi. Ku O-level tusomesa arts ne sciences ate A-level tusomesa sciences zokka. Omwana mulete ku The Science Foundation College. Ffe tusinga okusomesa sciences. Okumanya ebisingawo kuba ku 0753 827 09. The Science Foundation College, based on sciences and based for sciences.
Dr. Bosa is a teacher at the Science Foundation College, the best school that teaches sciences. At A-level, we teach sciences only. At O-level, we teach arts and sciences. Today, we are going to study Lotz-Law and fractional distillation. Suppose a mixture that contains 20% A, vapor pressure of A is 500 and 80% B, vapor pressure of B is 200, is boiled. The composition of the vapor can be determined as follows. From Lotz-Law, the vapor pressure of the solution is equal to partial pressure of A plus partial pressure of B. Partial pressure of A is equal to mole fraction of A times vapor pressure of A. Vapor pressure of solution will be equal to 20 over 100 times 500 plus 8 over 100 times 200. This is equal to 100 plus 160, which is equal to 260. The composition of the vapor is obtained from Dalton's law is equal to partial pressure of A over partial pressure of the total. So the composition of A in the vapor is equal to 100 over 260, which is equal to 0.4. And the composition of B will be equal to 160, the partial pressure of B divided by the total pressure, which is equal to 0.6. It should be noted that the total mole fraction is 1. When the mole fraction of A is 0.4, the mole fraction of B is 1 minus 0.4, which is equal to 0.6. It is observed that the composition of A, the more volatile component, increases in the vapor. We saw that in the mixture, the composition of A has got a mole fraction of 0.2. In the vapor, A has got a mole fraction of 0.4. So the composition of A in the vapor has increased. When the vapor is cooled, the distillate will contain the same composition as the vapor, say 40%. This liquid, if we boil it again, the composition of A in the vapor will increase, and definitely the mole fraction of A in the distillate will increase. If the distillate is boiled again, the composition of A keeps on increasing until the final vapor will contain pure A, which is a complete separation of A from the mixture. Let's carry out the calculation and see. We can present the results in the table. We have seen that when a liquid mixture containing the mole fraction of A 0.2 is boiled, the vapor given off containing the mole fraction of A as 0.4. The total vapor pressure was 260. When this vapor is cooled, the distillate given off will have the same composition. If we boil this liquid of mole fraction 0.4, then we can still get the mole fraction of the vapor the same way using Raoult's law. P total will be equal to 0.4 times 500 vapor pressure of A plus 0.6 the mole fraction of B times 200. This will be equal to 200 plus 120. This will be equal to 320. So the total vapor pressure from this mixture will be 320. Then the mole fraction of A in the vapor 2 will be equal to 200 over 320, and this one will be equal to 0.6. When you cool this vapor, the distillate given off will have the same composition, 0.6. If again you borrow this liquid D, P total, the new vapor pressure will be 0.6 times 500, the vapor pressure of A, plus 0.4 times 200. The total mole fraction is 1. When the mole fraction of A is 0.6, the mole fraction of B will be 0.4. Again, this will be equal to 300 plus 80, which will be equal to 380. Then the mole fraction of A in the third vapor will be equal to 300 over 380, which will be equal to 0.8. Will be 0.8. The total vapor pressure will be equal to 308. Again, when you cool this vapor, the distillate given off will contain 0.8A. If we boil this distillate once more, the vapor pressure of the mixture will be equal to 0.8 times 500, then plus 0.2 times 200. This will be equal to 400 plus 40, which will be equal to 440. Then the mole fraction of A in a vapor 4 will be equal to vapor pressure of A, which is 400 over 440, which will be equal to 0.9. The total mole fraction, the vapor pressure here is 400. In other words, when you boil a liquid D of mole fraction of A equal to 0.2, the vapor pressure of the solution will be 260. The mole fraction of any vapor will be 0.4. When you cool this vapor, it comes into a liquid, which is the same mole fraction 0.4. When you boil this liquid, the vapor pressure of the liquid will be 320. The mole fraction of it will be 0.6. We can say that as we continue boiling the distillate and cooling it, the composition of A in the vapor keep on increasing, and the vapor pressure of the solution also keep on increasing, meaning that the boiling point of the solution keep on decreasing. When you have to draw vapor pressure stroke composition curve, we shall have pure A on this side, then this is pure B. We have composition A having a higher vapor pressure. P naught A, we saw it was 500. P naught B, we saw it was 200. A liquid with high vapor pressure will have a low boiling point. So the boiling point of A will be lower than the boiling point of B. Boiling point of B. This is the boiling point of A. This one is temperature. This is 0.2A, 0.4A, 0.6A, 0.8A. A liquid which contains 0.2A here, or 0.8B, 0.8B because the thermal fraction is 1, will boil at a temperature lower than that one of B. Any temperature which is T1. It will give off a vapor of higher composition of A. When we cool the vapor, liquid D will give us another liquid D of the same composition, 0.4, but boiling at a lower temperature because the vapor pressure of that mixture will have a higher vapor pressure than the previous one. Then again, this liquid D will give you a vapor of a higher composition of A. When you cool this vapor, the liquid given off will have the same composition. When you boil this liquid, the vapor given off will have a higher composition of A, 0.8. When you cool that liquid, it will give the same composition. When we boil this liquid here, the vapor given off will have a higher composition, which is 0.9. Again, when you cool the vapor, the liquid will have the same composition. So, it means that when you plot these values on a graph, boiling point composition curve, we get two curves. We get a liquid curve, we get a vapor curve. We have said that a liquid that contains fraction 0.2A will boil at a certain temperature lower than the boiling point of B, will give up a vapor of higher composition of A, which is 0.4. When the vapor is cooled, it will give you a liquid of the same composition. If you boil this liquid D, the vapor given off will have a higher composition of A, 0.6. When we cool this vapor, the liquid will have the same composition. When you boil this liquid D, which will boil at a lower temperature because of higher vapor pressure, the vapor given off will be rich in A. Again, when you cool this vapor, we shall get a distillate of the same composition. Again, when you boil this liquid, the vapor given off will be rich in A. And when we cool this vapor, it will give us the same composition of the distillate. Further boiling and cooling the distillate will finally give us a distillate which contains pure A, which is complete separation. The question will be, explain how pure A can be obtained from a mixture that contain mole fraction of A equal to 0.2. That one, when a mixture that contains 0.2 mole fraction of A is boiled, the vapor and the distillate formed will contain a higher mole fraction of A. In this case, it was 0.4. When a liquid that contains 0.2 mole fraction of A is boiled, the vapor and the distillate given off will contain a higher mole fraction of A. In this case, 0.4. When the distillate in one is boiled, that contains 0.4 mole fraction of A is boiled, the vapor given off and the distillate will have higher mole fraction of A. In this case, the mole fraction of A has increased to 0.6. Repeated boiling and cooling of the vapor gives pure A as the final vapor and the distillate. And for this case, we have been able to separate A from B. B, explain how pure B can be obtained from a mixture that contains 20% B. 20% B, 80% A. So when a mixture that contains 20% B boiled, it will boil to give a residue that contains high percentage of B. Repeated boiling of the residue gives the final residue as pure B, that is complete separation. Sample question is 1. A compound A boiling point 272 degrees Celsius and the compound B boiling point 399 degrees Celsius form an ideal solution. Sketch a boiling point composition diagram for the mixture. Then you draw the axes. You put here pure A, this one is pure B. Here you have composition, here you have temperatures, degrees Celsius. A boils at 272. B boils at 399. Remember the boiling point composition curve of a mixture that obeys Raoult's law will have two curves. One is a liquid curve, the other one is a vapor curve. You put a title. This is boiling point composition diagram. Number 2, using the diagram, describe and explain how pure B can be obtained from a mixture that contains 50% B. So a mixture that contains 50%, when a liquid that contains 50% B is boiled, the residue given off will contain higher percentage of B. Continued boiling of the residue will finally give the final residue as pure B. Sketch vapor pressure composition curve of the mixture of A and B. Then we shall have the axes. This is A, this is B. Here we have composition. Here we have vapor pressure. A component with low boiling point will have a higher vapor pressure than a component with a high boiling point will have a low vapor pressure, which is P0 B. According to Raoult's law, The vapor pressure of the mixture will be a straight line. This is vapor pressure of mixture. Then according to what so the partial pressure of B is equal to mole fraction of B times P naught B. Similarly, according to Lot's law, the partial pressure of A is equal to mole fraction of A times vapor pressure of A. So our diagram will look like that. The vapor pressure of the mixture is the sum of partial pressures of A and B. The component with low boiling point will have a higher vapor pressure. The component with a high boiling point will have a lower vapor pressure. According to Lot's law, the vapor pressure of a component in a mixture varies linearly with its concentration. So we get a straight line for vapor pressure of the mixture, straight line for partial pressure of B, straight line for partial pressure of A. These are straight lines. 1. State Lot's law and mention its limitation. Lot's law states that the partial pressure of a component in a mixture is a product of its mole fraction and the vapor pressure of the pure component at the same temperature. Limitation. The components must have equal forces of attraction between like and unlike molecules. 2. The enthalpy of formation of the mixture is 0. In other words, there is no change in temperature when the mixture is formed between the two components. And 3, the volume of the mixture is equal to the sum of the volumes of the components, or there must be no change in the volume when a mixture is formed. 2. Sketch boiling point composition curve for two liquids A and B more volatile than A that obey Lot's law. The boiling point composition curve of a mixture that obeys Lot's law has got two curves, has got a vapor curve and then a liquid curve. In between the vapor curve and the liquid curve, a liquid and the vapor are in equilibrium. Then vertical axis is temperature, horizontal axis is composition. B being more volatile than A, B being more volatile than A means that the boiling point of B is lower than that one of A. 3. Discuss with aid of a diagram in 2 above what would happen to the typical mixture in 2 above is fractionally distilled. Boiling a liquid of say composition Z will give off a vapor which is richer in B. When the vapor in A is cooled, the distillate will have the same composition. Continued boiling and cooling the vapor from distillate give pure B in vapor or distillate, which is a complete separation. Secondly, boiling a mixture of composition Z gives off a residue which is richer in A. Continued boiling of the residue will give you a final residue as pure A. 3. The boiling point of liquids Y and Z are 368 and 395 degrees Celsius respectively. Sketch a labeled boiling composition diagram for the mixture of the liquids. When the liquids Y and Z obey Lot's law, then the boiling point composition diagrams must have two curves. The upper curve is the vapor curve, the lower curve is the liquid curve. The horizontal axis is composition, the vertical axis is temperature. The boiling point of Y is 368, the boiling point of Z is 395. 2. Using the diagram, describe how pure Z can be obtained from the mixture that contains 50%. This is 50%. Boiling a liquid that contains 50% Z will give a residue with a higher concentration of Z. Boiling a mixture that contains 50% Z gives off a residue that is richer in Z. Z is the least volatile component. So boiling a mixture that contains 50% Z will give a residue which is richer in Z. Continued boiling of the residue gives the final residue as pure Z.